Uh, okay. Hello everyone. In this video, I want to introduce you to the project I'm working on for CPEN512 course. I'm trying to explain data level parallelism and fluid level parallelism somehow for an image dithering algorithm called Floyd-Steinberg dithering. I picked up this algorithm from EMBC benchmarks, which develops industry standard benchmarks for the hardware and software. You can read more about the EMBC benchmarks and EMBC community in this link. So what does Floyd-Steinberg dithering do? It's typically used when you need to reduce the number of colors in an image and still retain a reasonable perception of relative color and brightness levels. This is achieved through pixel dithering. In other words, an approximation of the required color in each area of the image is achieved with a pattern of pixels. The results here becomes a trade-off. What you lose is the overall level of detail, but what you gain is a reasonable color representation of the original image. For example, here you can see the picture of David statue on the original one on the left. It's a grayscale image, which means each pixel only has a value between 0 and 255. You need 8 bits for each pixel. And you can see the effect of different dithering filters on the picture. For example, order dithering, Floyd-Steinberg dithering, and Jarvis dithering. And these pictures are 8 times more compressed than the original picture, because you only need to store 1 bit per pixels. It's commonly used by this dithering algorithm, commonly used by image manipulation software for example, when an image is converted into GIF format that is restricted to a maximum of 256 colors. The algorithm. The original benchmark source code only works on the grayscale images. So let's define the algorithm on grayscale images. The algorithm itself is quite simple. What you have are 3 buffers: the original image, an error diffusion buffer, the destination image. The algorithm defines a method of traversing over an image and for each pixel determining an error. For example, here the first loop traverses the image from the top to the bottom, and the second loop, the nested loop, traverses image from the left to the right. And for each pixel, you are going to calculate a new value based on the current value and the error value of that pixel. So next, you are going to make a comparison between the new value and a threshold. If the value is greater than the threshold, the pixel value is set to the maximum, to 255, and you're going to save the difference. And if the value is less than the threshold, the pixel value is going to be 0, and the difference is set to the old pixel value. Then you need to propagate this difference. You can think of it as the brightness. You want to propagate this brightness to the other to the nearest pixel, nearest neighbors of that pixel, by some ratio, of course. So for each pixel, you have to calculate the error, and then you have to propagate the error to the 4 pixels, the one to the right and the 3 on the bottom of the pixel, as follows you can see in this picture. So is there any hope for polarization here? Perhaps this algorithm is better tackled by the CPU. But imagine the Floyd-Steinberg filter was part of a filter chain, so where there was significant benefit for running the other filters before and after this one on another platform like a GPU. Here, we would need some synchronization points either side of the Floyd-Steinberg filter, and these are potentially quite expensive just to transfer the Floyd-Steinberg algorithm to the CPU. So let's look at the algorithm again and see what we might be able to do here. We can see that the only thing stopping an individual pixel being processed is whether its related error buffer value has been written to by all 4 pixels. For example, here you can see the C2 pixel, and it needs the 1. It needs the 1 on the left and the 3 pixels uh, 3 pixels above as follows. Uh, it means that if we want to process pixel C2, we have to wait until B1, C1, B1, C1, and D1 and B2 have finished, as these all writes values into C2's error buffer location. So one way we can exploit data third level parallelism for this algorithm is to associate a thread to each row. For example, thread I is associated with row I, and the thread I can start execution whenever thread I minus 1 is 2 steps ahead of the thread I. For example, here you can see the thread 0 is 2 steps ahead of the thread 1, so the thread 1 can start execution. So you need some variables, some shared variables for each thread to synchronize thread to do their jobs. But how can we exploit the data level parallelism here? For data level parallelism, we can use a one-dimensional convolutional filter operation to calculate error propagated from row I to row I plus 1. Let's say we perform the row I, so we know the error buffer of the row I, and now we can calculate the errors that propagate from this row to the next row by only sliding this 1 by 3 filter on this error buffer. And it's really simple to implement on a SIMD vector machine, because you can just multiply each the element to the row buffer and then shift the output and then just add up the vectors. I've implemented the SIMD version for this to exploit data level parallelism on MXP. My goal is to implement my code on real hardware, on real FPGA, on real MXP hardware. Actually, I changed the benchmark a little bit to support RGB pictures, to support BMP files. This is the output of my code for MXP. I do not have the final results yet. I'm still working on it. So this is my presentation till now. I hope you enjoy. I hope you enjoyed.